Okay, let's have a class, and I will talk about like 25 minutes to talk about glycerides, triglycerides, and Ian will talk about the manufacturing of the chocolate. And we're also going to do a video recording, and you can see that later on. And this is first time we have a student doing in the classroom about manufacturing of the chocolate. So let's talk about something we already said, the fatty acids. And we talk about these fatty acids, and this is, we mentioned there is a long chain. I'll just give you an example. We have COOH, which is carboxy ends, and with a very long chain of basically CH2, which is carbon hydrogen bonds, and end up with CH3. Okay, that's a methyl end. And we mentioned about several, you should be very familiar so far, because it is important. We're using short hand description to describe it. If I see C60, what this means? It's palmitic acids. And if it's C18, that's stearic acids. And these two obviously are saturated fatty acids, there's no double bonds. Then we go C18, comma 1, this is oleic acids. And if we go C18, 2, that is linoleic acid. And if we go C18, comma 3, that is linolenic acids. And all of those three, make sure you know about this, because when we talk about lipids oxidation, on Thursday we're going to mention that again. Okay, now there is one thing I have to correct it about that is, let's say we had oleic acids. Let's start from COH. So oleic acids, what it looks like. We're going to do the couple, go here, 1, 2, 3, H3. Okay, so we see it 2, 3, 4, 5, 6. We have to do one more. 6. Could go 7, 8. We go down. Go here. Okay, that's 9, 10, 11, 12, 13, 14, 15, 16, 17, and go here, 18. And I said this is a mono unsaturated fatty acids, because we have bonds up here, okay? And they will go through a process called hydrogenation. And the hydrogenation will go through a process which is add hydrogen there. However, they always have a transition step from cis goes to trans. So what going to be the trans looks like? This is COOH. We're going to be always do like that. They always do like that. So we do 2, 3, 4, 5, 6, 7, 8, 9, 10. So what are going to be there? Bonds go? So bonds going to go here. Okay? Then we have 11, 12, 13, 14, 15, 16, 17, and finally goes to here. Okay? That's from cis to trans. That's oleic acids. Okay? You can figure out the structure of that later on, because we're going to mention it. So we mentioned this part, fatty acids, but we left the other part I haven't mentioned. If we talk about triglycerides, okay, so we basically mentioned the part, yes, CHCOO1, CH, we can say OH, okay, R2, and R3, and this is we skip it, just use R1, R2, R3. This is called fatty acids. Then we need to add something there. This something we call, it is a very interesting stuff. You have 3 carbon, you have H there, you have H there, but very interesting. And I should have put on the other way, because it is easy for you to understand. I put on the other way, which is OH, 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 and this H, this H, this H, and H. So what is this one? Glycerol. So what is glycerol? This is the one we already mentioned it before. This is called cryoprotectants. Because this could be combined with sodium triphosphates and using as to frozen storage of bacteria. Remember, glycerol bacteria could put there and at -80 degrees Celsius will protect the bacteria cell wall. So we already talked about this, the glycerol. Now, glycerol is very interesting. If you look at this structure, what you find, this center is 2 of them are exactly the same. This side, bottom and above are the same, and only 2 sides are different. So, if we draw another picture, what is it going to be looks like? CH2, OH, this CH2, OH, we can draw like that. So what this means, the C right in the middle is 2 of the 4 are same. That means it is a chiral structure. Okay, it's a chiral structure. Now, how we do it, we can just draw a picture we can just draw like this. Like a mirror. Okay, so we give them a name called enantiomer. What this means a chiral from a mirror create isomers. So that's very interesting. Now, if I have a fatty acids, I have a glycerol, they could be reacted. This is what we already know. How they reacted with each other, they're going to lose the water. And these things could combine, these things could combine, these things could combine and become a water and gum. Okay, so what they going to be looks like? What their looks like is kind of very interesting results. You're going to have CH2, O1, then you have CHO, O2, and CH2O, and O3. This becomes triglycerides. Now, we want to mention that we always call it is triglycerides because triglycerides could be using as a diets or as a food component. But we also need to know it could be monoglycerides, which means only R1 there. And it also could be diglycerides. Okay, what are these components? These are components most of the time are not in foods as a diet. This is usually we call it's an emulsifier. So what the emulsifier? They will be break down tension between liquid with air, liquid with liquid, or liquid with oil. So that's very interesting, okay? Now let's talk about this. Let's talk about this very interesting stuff. CH2O, O1, CHO, O2, CH2O, and R3. Let's talk about this triglycerides. These triglycerides, they have a 3 location, R1, R2, R3. And we most of the time label them as SN1, SN2, and SN3. Now what is this SN means? stereo specific number. STERE, stereo specific number. That's why we call it an SN, stereo specific number, S and N. These 3 locations in most of the fatty triglycerides, it's more specific. Long time ago, in 1950s, there was a scientist called Heinrich. He think no matter what happened, this is R1 to R3, it is even distributed. So what this means, this tells us if I have a GAX2, that means I'm going to measure the amount of the A components. I will see this around 35% more, or more percent. If I see it is GA2X, this will be 35 to 70 more percent. If I see GA3, that means it's more than 70 more percent. If it's evenly distributed. However, later on, in 1960, a very important guy, Van der Waal, you know that, he mentioned about that. In different products, the fatty acids, they are actually randomly distributed. But this randomly distribution is just not like whatever you like to do. It is conditional. So we call it a conditionally randomly distributed. So what this means, so we could give you several examples. Okay, number 1 example. If we are talking about the products, which is let's say, which is plant oil. And we will see the SN2 position most likely is polyunsaturated fatty acids. However, SN1, SN3, usually it's saturated fatty acids. This is the first example. The second example is lard. This is from the pig. We call it a pig oil. And this guy is very interesting. What you see, for pig oil, SN1, SN3 is oleic acids. That's why I draw here. It's oleic acids, it's unsaturated fatty acids, and right in the middle is stearic acids. I just want to make sure it is palmitic acids right in the middle. So SN2 is palmitic acids. And because of this magic stuff, lard has two positions, has unsaturated fatty acids. So there is a tons of research has been doing, showing if you eat certain amount of the pig fat or the pig meat, it is actually will be beneficial for the prevent cardiovascular disease compared to eat like beef or lamb, because those are most of them are stearic acids or palmitic acids. Lots of research to do because SN1, SN2, 3 is oleic acids. It's unsaturated fatty acids. Now number 3, what we're going to talk about is cocoa butter. Okay, this is a material which is an original resource which is making as a chocolate. So what's the components of that? This components SN1, SN3 basically is palmitic acids, or that could be stearic acids. Anyhow, it is saturated fatty acids. SN2 is oleic acids. That's the reason some people say if you eat black chocolate, actually will be beneficial for your health a little bit. Even better for, combined with other things, for the metabolic of your body is to prevent obesity. Lots of people say. They also could be prevent cardiovascular disease. But more important for this structure, do you find that chocolate has something very special? We do that all the time, but we never noticed it. It is solid at 25 degrees Celsius, room temperature, but very magic. If you put it in your mouth, it will be melting at 35, 37 degrees Celsius. This is the magic. And they said because of the oleic acids in the right of the middle. Okay, so these are the things which tells you these 3 locations, it is somehow it is very important. Now we mentioned about this chiral structure. For the triglycerides, we also could be talking about that, which is C in here is all is CH the C on the top is CH2 OO1. This is we call stereospecific number 1. This could be R2 OO. This will be H. And then this go down here is CH2 OO3. Now what they secretly looks like that, it somehow looks like this. So what they say, in the middle on the top, this looks like that. Give you a feeling like you have an airline, have a plane at the airport, they fly away. But in the middle too, what happened? Like this, like they're flying back to the airport and landed. So this is, we also call it wedge form. This is related to the chiral structure. Okay? Now the last thing, do you mind this little bit? The last thing before we talk about the chocolate manufacturing, we also want to mention a little bit about how we're going to name these things. How we do the nomenclature. There is a different way we do. Okay, so nomenclature number 1. Lots of the times we don't really care. what kind of the fatty acids it is in the triglycerides. We only care about are they saturated or unsaturated. So we could even write SSS, UUU, or SUS. So what this means, we know all of these are tri-saturated fatty acids. And this is a unsaturated fatty acids. And this is stereospecific number 1. Number 2, SN2 is unsaturated. And this is very easy. The first name system. The second name system. It's pretty simple. Some of the food products we know they all combined with stearic acids. So we write SSS, or we write PPP. That's why we call it a tri-stearic acid. This is tri-palmitic acids, and we already know that. Okay, that's something we simple. Then we move on to the third stage. We know the 3 locations, and we know there are 3 different fatty acids. However, we don't know their stereospecific number. So, what are we going to do? Let's say I had palmitic acids. I have oleic acids. I have a stearic acids. What we do? The nomenclature system is IC changed to OYL. So what are we going to call this? We'll call palmitol oleo stereo, and we say glycerol. That's one of the way we do. Okay, then we move on to the last stage. We not only know what kind of fatty acids it is, we only know the stereospecific number. For example, we know the SA1 is palmitic acids, and we know SN2 is oleic acids, and we know SN3 is stereospecific, stearic acids. So how we do it? You see, the other way what we could do is we say 1 palmitol, 2 oleo, and 3 sterol. Don't forget the SN, stereospecific number, and glycerol. That's another way to do it. Okay, now people think about this is too long. Okay, we don't want that long. We could do 1, 2, 3. That's 16. The palmitic acid is 16. 16, and this is 0. And lots of the time, we could also say just easy. So that's the way we could do the nomenclature system. Okay? So that's what I have. Basically, is for triglycerides, some of the introduction. Now, before we go, let Ian talk about that. I have a last thing I want to mention. When you look at here, there is a double bond. So I give you a very easy example. I have CH2, CH, fatty acids. How do we know what's the level of unsaturation? How we do it? We then let them react with iodine. Okay, very simple. What you're gonna get? CH2, CH, CH, CH2. So you're gonna add iodine there. This comes out to a very important thing, is iodine value. This could be used to indicate unsaturation and vulnerability of fatty acids to lipids oxidation, which we will talk about on Thursday. So this comes up with some of the basic knowledge. What do you think of the iodine value of saturated fatty acids? Saturated fatty acids, the iodine value obviously is 0. A very long chain unsaturated fatty acids. Let's say some of them are coming from chicken or turkey, maybe. Chicken or turkey meat. That could be as high as 136 to 140 value. What do you think of the iodine value of cocoa butter? Because cocoa butter, we only have oleic acids in the middle, so relatively small is 30 to 40. So that's a very easiest way we could be measuring the unsaturation of those fatty acids. Okay? Okay, that's all I have. And then the next one, we're going to move the stage to Ian. He will talk about all of the chocolate manufacturing, how we're going to do it. So we're going to open the projector down. I'll do that one. So I will be just, you can log in or just move this at the back. Okay. Let you can be. You should be touch that one. It will be on. Yes, I think it's working right now. Yes, just go ahead and grab some of the chocolate. Then he will be very easy to explain to you what happens. Should at least grab some. That's a very good stuff.
How did that go? Did you get a lot of people?
118
name of the tree that cocoa comes from is Theobroma cacao. It's a tropical evergreen tree. The products we get are, like I said, the cacao bean, cacao paste, cocoa butter, and cocoa solids. The pods grow against the tree, similar to bananas. They don't grow on the branches. The varieties of the Theobroma cacao tree are Criollo, Forastero, Trinitario, and Nacional. They are all over the place in South America, Brazil, Africa, Colombia, Mexico, and there are a couple little sub varieties, but those four are the main ones. The one that dominates worldwide production is the Forastero. These beans are from Uganda, and the beans that you have in the chocolate on your desk, and so I would bet that they are probably Forastero variety. So, as I said, the trees grow the pods. The pods contain the beans. These are the unfermented cacao beans. I'll address that. You may have heard cacao versus cocoa. Is anyone familiar with the difference? So the difference is, once it goes through fermentation, it becomes cocoa. Before it goes through fermentation, it is cacao. So, beans, like I said, are fermented, dried, and roasted. These are the roasted beans, like in that bag. The roasted beans are shelled and winnowed, creating nibs. And then the nibs are ground and melanged to create the chocolate liqueur, or liquor, and the liquor is conched and then tempered. So right now, this process that you see is the melanging or grinding process. You're welcome to come take a look. Take this off. Basically, this spins. There's a granite stone in the bottom, and there are two granite wheels that turn as it spins. And the beans are ground so fine that it becomes the liquid that we all know as chocolate. We've talked about approximate composition a little bit here. These are the approximate compositions of various origins of beans. I had to figure the carbohydrate by difference because this paper only talked about the protein and the lipid content, but the carbohydrate includes the monosaccharides, disaccharides that we've talked about, and fiber. And so that's why it's so high. Actually, pure cocoa beans are quite high in fiber, like any seed. They're delicious and they're quite high in fiber. So let's start with fermentation. Fermentation uses yeast and bacteria that grows in the pulp. So the pulp is this white section surrounding the bean. And the yeast and bacteria, they continue to grow and proliferate for about 7 days. During those 7 days, the 3 phases of fermentation take place. Fermentation is key for the production of the precursors that are development of the aroma in chocolate, Strecker, degradation, and Maillard reactions like we talked about, as well as caramelization. So during phase 1, anaerobic yeasts dominate. They drop the pH. It's like I said, an anaerobic process, so a very low oxygen availability. And these yeasts activate carboxypeptidase and aspartic endoproteases. We learned about proteases that break up proteins and amino acids. They free amino acids. And of these, leucine, alanine, and phenylalanine are particularly responsible for Strecker aldehydes and pyrazines. And those are, again, more of the aromatic compounds. The second phase, lactic acid bacteria are active, and those convert the sugars into organic acid, specifically lactic acid. And then after about 96 hours in the third phase, acetic acid takes the alcohols that were a result of the yeast's fermentation and converts that into acetic acid as well. So there's a lot of acetic acid, and you'll find later acetic acid is one of the main aromatic compounds that is in chocolate. It gives it an astringent, almost tangy flavor, And so I really like this picture. It kind of doesn't make sense unless you walk through everything, but it's a great picture of what's happening from fermentation to roasting to almost to grinding. So we start with carbohydrates, hemicelluloses, which is the pulp, and organic acids, which form from the fermentation to the sugars, the acids being formed. So this is the pulp around that white section of the bean, and then this line is the bean itself. So from the bean, we get those proteins and peptides that I talked about, the sugars, everything broken down during the fermentation process. That then combined with the microbial activity, the yeast activity that we talked about, produce lactic acid, ethanol, and then heat with exothermic reactions from that third phase. At the end of the process, we're left with carbon dioxide and water, and then the bean is dried up and ready, well, not dried up, but the pulp degrades to kind of wrap almost like plastic wrap around the bean, and then the bean is ready for drying and roasting. And so these are the beans that I put, and Tiffany helped me, in the refiner yesterday. It was that exact form, and after 24 hours, that's what you get. So it's so finely ground. We put a little cocoa butter in there, a little sugar, and that's it. So what I've talked about proteins and I've talked about carbs a little bit, but obviously there's carbs in there. There's plant material, sucrose is naturally formed, fructose. We know that Maillard reactions take place with heat, which would be the roasting, and protein and carbohydrates. So the Maillard reaction takes place, it's a pretty high, 120, 140 degrees Celsius, and takes place between the carbonyl group of the reducing sugars and the amino group from the free amino acids or proteins. Now, some, like I said, some amines, some free amino acids are formed during fermentation, and then some aldehydes, but roasting, and in particular the Strecker degradation and Maillard reaction, is more effective at forming those aldehydes than fermentation. And so, like we know, this is like a super broad overview, but sugars can be converted to Schiff bases, can be degraded to Strecker aldehydes. And this step right here is called thermal decarboxylation, and that's again with the roasting at a very high temperature. And like I said, the caramelization also happens with sucrose and reducing sugars, and gives us the beautiful brown color and more aromatic compounds that we love about chocolate. So back to aromatic compounds, I tried to get everything relevant to African origin beans, because these are Ugandan, so Eastern Africa. Of all, and there are many, many, many more aromatic compounds that exist in chocolate, but these 6 were deemed by the authors of this paper to be greater than 1 OAV, which is like an olfactory value. They essentially quantified the presence of these molecules in terms of how they taste and the volume of flavor, we'll say, and they quantified it and they gave us the scale. So 6 is not that many. And below 1, they said that you probably wouldn't be able to pick it up in a normal human palate. If we look at commercially available chocolate, There's too many, I was too lazy to type all those out. And look at the levels. 840 OAV, or acetic acid was 720, in the prior slide it was 52 something, 52 point something. So if you haven't tasted your chocolate on your desk already, feel free to do so. The difference between commercially available chocolate and this chocolate is what's called single origin. And so all of these beans, the beans that are in the grinder and the beans that made the chocolate on your desk, come from one farm, one batch. So they were grown under the same circumstances, the same sunlight, water, fertilization. It's just like coffee, just like wine. They were roasted at the same time. They were fermented for the same amount of time. So those flavoring compounds had the same amount of time to develop and to mature and to degrade and all the other processes that we talked about. Whereas commercially available chocolate, they get beans from all over the place. And they put them all together, and then they add other stuff. They add vanillin. Vanillin isn't even a naturally occurring flavonoid in chocolate, but they add it to kind of level out the insane amount of acetic acid. And that's why what you're tasting right now is different than Hershey's, or even like a really high quality chocolate that you could get from the store. You taste like tangy notes and maybe like some raisin, cherry, I've heard people say. So it's those developments of those compounds through the caramelization. Caramelization happens in all of them, but particularly the growing mediums, the fertilization, just the growing environment, and then fermenting in the same batch, drying and roasting in the same batch, that gives us those wonderful flavoring compounds. So this is a picture from Utah State University when I went. This is their refiner. It's the same machine, just giant, and they named it Augustus Gloop. And it was actually a pretty phenomenal experience to be there. So refining is more a physical process than a chemical process, because it takes those beans and breaks them down to particles that are ideally 15 to 25 micrometers. Very, very small. It's so small that the human palate, like your tongue cannot discern the difference in this range. So basically, refining, like I said in the beginning, a little sugar went in there, the beans, a little cocoa butter. So we had to break down those sugars, we had to break down those cocoa solids. Once they're broken down and kind of slightly ground, they're considered cocoa nibs, and then the cocoa liqueur is what's currently spitting in the refiner. The cocoa butter is in the nibs themselves. It's located in the cell wall, the shell, and the germ. Some fatty acid oxidation occurs during fermentation and roasting, but it's really protected in, they call them high molecular weight oligosaccharides, in the plant wall and the cell matter of the plant itself. And so it's protected, and so it doesn't taste off, it doesn't taste rancid like an oxidized fat or oil would. But during the refining process, we break all that down and release the cocoa butter. It's actually kind of neat. You can tell, you can see it kind of goes like, it looks like dirt mixing, and it gets grainy, and then sand, and then there's a definite, Tiffany may have observed it with me, there's a definite part where you can tell those structures are broken, and it gets oily on its own. And then you add more oil, and then it turns into like a fluid system. But that oily process is exactly what's happening when you break down those cell walls. Shear force must be used to release these, the cocoa butters. It can't be crushing or grinding. Well, I guess grinding is shear force, but crushing particularly or cutting, it's got to be a shear force. I think that has to do with the friction, because as we learn, Cocoa butter is solid at room temperature, cold temperatures. So you want it to be an oil state. So then your flavonoids, your flavor particles, your sugar particles can travel freely in that system to disperse evenly, and then once the system solidifies, you have a good bite where it's not, oh, there's a small, it would be on a almost molecular level, but you would still be able to tell grainy, the flavors wouldn't be as even. Conching is a process, we can't do it here. It's kind of one and done. The refining and conching process are being taken care of at the same time with our process here. But it involves heating and aerating the liquor. This introduces oxygen, and as those of us in food know, introducing oxygen on a very small scale really, really helps flavor development and opening up those flavor compounds. Because aromatic compounds are exactly that. They're aromatic. They're based in the air. So we need that. You may have seen the TikTok. Gotta air it. Anyway. It also removes some volatile short-chain fatty acids. The fatty acids that are smaller than the 16 carbon that we discussed. Those will dissolve. Those will